Geometry 2-7, Proving Segment Relationships. Proving segment relationships. Okay, so we're going to look at another postulate, and again, I want you to not be concerned about the number here. So in the book, this is called postulate 2.8, ruler postulate. And all this says is the points on a line or a line segment so if you have points on a line or on a line segment, can be measured. They can be measured. And when they are measured, the distance between them will be positive, and it'll be a real number. And so if I have a line segment that's like this, line AB, I could put a ruler up to it, and I could measure that line segment. That's all it's saying. Now let's look at another one. 2.9, segment addition postulate. The segment addition postulate says if A, B, and C are collinear, so remember collinear means they're all on the same line. So if points A, B, and C are collinear, then point B is between A and C if and only if AB plus BC equals AC. So notice how there's no segment on top of this. This is just saying the distance between A and B plus the distance between B and C equals AC. So let's draw a diagram and see if that can be helpful in understanding what we're trying to say. So we'll say this is A, and this is B, and this is point C. This distance here between A and B is distance AB. This distance here is distance BC. And then this distance here altogether is AC. So if I add AB and BC, when I add those together, I get AC, I get the total. So now I believe for the rest of these notes, we're just going to be trying to do some proofs. So let's do a few proofs together. Prove that if CE is congruent to FE and ED, segment ED is congruent to segment EG, then, notice we have an if-then statement, then segment CD is congruent to segment FG. And, oh, that's it. Okay. So we're given that segment CE is congruent to segment FE, and segment ED is congruent to segment EG. And we were being asked to prove this then statement, CD is congruent to FG. And we have a diagram here to draw. And let's see. This point on the left is F, up on top is C, over to the right is G, down at the bottom is D, and in the middle is E. So let's mark up this chart a little bit here. CE is congruent to FE, so CE here is congruent to FE here. Okay? And ED is congruent to EG. So this segment is congruent to this segment. And so we are trying to prove that CD is congruent to FG. Okay, so we're going to set up our two-column proof. We're going to have our statements on one side and our reasons on the other side. Now this proof might end up being a little bit complicated, so try to stick with me here. Statement. So I'm going to start with segment CE is congruent to segment FE, and segment ED is congruent to segment EG. And I'm just stating the given. My reason is given. Now I'm going to use my statement of congruence, definition of congruence here, to say these two segments are congruent, which means that they are the same length. So CE is the same length as FE, and ED is the same length as EG. Because they're congruent, I know that they're the same length, and so that is the definition of congruence. And I'm just going to draw the little congruence sign. Okay, now I'm going to ignore this a little bit for just a minute, and I'm going to use my segment addition postulate. And I'm going to say that CE plus ED equals CD, and I'm going to say FE plus EG equals FG. So I'm just going to say this segment plus this segment equals the whole thing. This segment plus this segment equals the whole segment. So I'm just going to say that because I'm trying to set myself up so that I can say this segment is congruent to this segment, and you'll see how in just a second. So CE plus ED equals CD, and FE plus EG equals FG. So this little segment plus this big segment equals the longer one. This little one plus this bigger one equals that one. And this is the segment addition postulate. Segment addition postulate. Okay, now here's the part where it gets a little bit tricky. I am going to say, I'm going to do some substitution here. So I am going to say that FE plus EG equals CD. and I'm going to say that CE plus ED equals FG. So here's what I'm saying. I'm saying that FE plus EG equals this segment. So before I said this one plus this one equals this whole thing. Now I'm going to say this one plus this one equals this one. And this one plus this one equals this one. How can I do that? I do that by substitution. And the reason this works is because I already know that CE equals FE and ED equals EG. So I can plug in CE. So before this was CE plus ED here equals CD. I can plug in CE for FE. I can just put that right in there. And I can plug in FE for CD or for CE. I can just switch those two because they're equal. Same thing with this one, ED, I can plug in right here where it used to be EG because they're equal. And I can take EG and I can plug that in right there because it used to be ED, but ED and EG are equal. I know this may be quite confusing, but it's a lot of letters and everything. We'll do some more after this as well. And so now I've said this, these two smaller segments equals this longer segment. These two smaller segments equal this larger segment. These two equal that one. Now, I want to say CG equals FG. CD equals FG. I can say that by substitution as well. And the reason I can say that is because up here, I've got CE plus ED equals CD. And I've got CE plus ED down here equals FG. So that means I can just switch. I can take this CD here and I can plug it in. I can substitute it for CE plus ED because I already know that CE plus ED equals CD. So CE plus ED, I can substitute CD for that expression there. And now CD equals FG. And I want it to be a congruency statement instead of an equals here. So I just need to change it from the distance. We're talking about distance here, and we're talking about congruence of segments here. So we have the definition of congruence. Whew. There we go. There's one down. Let's do another one. And we'll do this together. Let's see. Another example. We are given segment JL is congruent to segment KM, and we are asked to prove that segment JK is congruent to segment LM. So let's draw the diagram that comes along with this. This is JKLM, and we are given that JL is congruent to KM. So these two, this J to L and K to M are congruent. Now we don't know what's going on with this KL here, but we want to find out that JK, we want to prove that JK is congruent to LM. We want to prove that these two segments are congruent. All right, let's try it. Statements. and reasons. I've got a 2-column proof going here. So the first thing I'm going to write is my given JL is congruent to KM. Those segments are congruent, and I'm going to say that is the given. Now I'm going to translate this to distance. So I'm going to say JL equals KM, definition of congruence. So now I have changed this from talking about line segments to talking about distances between points. Now, here's where this one gets, well, this one is a little tricky. All of these proofs can be fairly tricky. So just try to hang in there and maybe watch the video a couple times and stuff so that you can see what we're trying to do here. So we're going to write JK plus KL equals JL. So JK plus KL equals JL. So all we're saying, we're using this segment addition postulate to say that JK plus KL equals JL. And then we're also going to write, as part of this same step, KL plus LM equals KM. KL plus LM equals KM. And so we're going to try to prove here, what we're trying to prove that JK and LM are congruent. So we need to write some true statements here that we might be able to work with in order to say that these two are congruent. Okay. Now, we are going to now need to, this is where this gets a little bit nuts here. We are going to take this equation and we're going to subtract KL from both sides. And we're going to take this equation and we're going to subtract, oh, well, maybe we're not yet, actually. Let's just do this one first. JK plus KL minus KL equals JL minus KL. So this is the subtraction property of equality. Oh, I should say subtract with a subtracting sign. So when I do that, KL minus KL goes away, and I end up with JK equals JL minus KL. All right, so I have JK equals JL minus KL. Now I'm also going to do the same thing with this LM. So if I have KL plus LM, I'm going to subtract KL from that side, and I've got KM. I've got to subtract KL from both sides. Oops, subtract, not add. And so these KLs on this side go away, and I end up with LM equals, because those KLs, I subtract KL from KL, which makes it 0. So I have LM equals KM minus KL. So I have these two equations, and I use the subtraction property of equality. What I do to one side, I do to the other side. Okay. Now, I know that JL is congruent to KM. So I've got JL here and KM here. Okay. So I'm going to say JK equals KM minus KL by substitution. So I've taken this equation, and since JL equals KM, I can just plug in Km or substitute Km for JL. So I end up this same equation right here, except for I've replaced JL with Km. So JK equals Km minus KL. And now I've got JK equals LM. How did that happen? Because I have KL, so I have LM is right here, right? LM. If I have Km, this whole segment, and I subtract KL from it, that's this segment, then I end up with LM. So if I have Km, I subtract KL, then I end up with LM. So that means Km minus KL equals LM. And so this is by substitution. We could probably use our segment addition postulate to help us with that as well, but let's just call it substitution. That's what they put it in the book, I believe. Substitution. And now I just say JK, segment JK is congruent to segment LM, which is what I'm trying to prove, and this is the definition of congruence, or congruent segments. Whew, a rough one, huh? Let's see if we, there is a little bit more notes that I need to put at the bottom of this. A theorem, and then hopefully we can do one more. So I'm going to stop the video here, and then we'll pick it up in just a minute because I want to add a little bit more here. Okay.